here's the catchy point, they don't have the same distribution of the mass, right? The mass on the hoop, all of it is out here at the outer perimeter or circumference of the hoop. Whereas the disk, the mass is spread out through the whole object. It's true, some of the mass is out here at the perimeter or circumference, but a lot of it is more on the interior parts as it rotates. So here's my question. Do these two objects rotate the same? That is, if I put them on that hill and I race them down the hill, is it a tie? Do they both rotate just as easy? Because they are the same diameter, they are the same mass, they are the same color, therefore they rotate just as easy? Or is one easier to rotate than the other? And if so, which one? And let me have you think about that for a second. But this is a good experiment to point out that the rotational inertia doesn't just depend on the mass. Yes, they have the same mass, 600 grams. But here's the key. The mass is not at the same location. For the hoop, the mass is out far. All of the mass is out far. That would be like taking these and moving them out so that all the mass is out far. But for this one, some of the mass is out far, but a lot of it is inside. So this would be like leaving maybe two of them out far and bringing the others two kind of close in. And since the rotational inertia depends on its location, I would say this configuration, that is this configuration, has a smaller rotational inertia. And I would think this one is easier to rotate than this one, because this one, all the mass is out here. Here, only some of it is out at the perimeter. Most of it is inside. So, if I'm right, then when I race them, they will not be a tie. And in fact, as I race them, if what I'm thinking is correct, the disk should spin, and that is rotate down the hill a little bit easier, and therefore a little bit faster than this one. So I'll race them and see which one wins. 1, 2, 3, go. And sure enough, the disk wins the hoop. And so it does go a little bit faster. All right, so we can finally finish this equation of Newton's second law here. And so right here, let me put then net torque goes in the numerator. So again, if you want to know what the acceleration of an object is, you'll have to, again, figure out the net torque. And I'll say it again, torque is more than force. But you would also have to divide that by this rotational inertia, which we are going to use this symbol I for. And so that will be our equation for a rotating object. And in fact, as I keep talking about the experiment we're going to do tomorrow, we're going to move the I to this side and the alpha underneath, because in lab, what we will measure is the net torque, and we will also measure the angular acceleration. And so if we know those two, we can then calculate the moment of inertia. Oh, I'm sorry, that's a math term. Your author calls it rotational inertia. But because it has a square in it, that's a mathematical way of saying a second moment. And so the moment has to do with distance, and when it's raised to a power of 2. And so math people like to call this a second moment of inertia. And so we kind of mix those two together. Rotational inertia, second moment of inertia. Sometimes we get lazy and we just call it moment of inertia. Or we add an S, we make it plural. We call it moments of inertia. That's probably the most popular one, moments of inertia. But I like what your author does. He calls it a rotational inertia, and so I'll stick to that because, again, it has to do with the inertia of a rotating object. All right, well, I see I've used a lot of time for those two and to get to Newton's second law, but like I said, I think it really needs it. And in fact, it really then begins to show up here, if you can kind of get the gist for this. That's why I grabbed this big block of wood. In fact, let me just give myself a little bit of space up here and say, all right, what if I did the following? What if I took this big block, and maybe I'll go this direction here so you can see it well on camera, and I push it. Maybe I'll just kind of use this string holder here to push it. If I push it right at its center, as opposed to pushing it on its edge, do you see a difference here? Do you see how when I was pushing it on its edge, it rotated? And I pushed it at its center, it just translated? Let me ask you again. To make something translate, you need a force. But to make something to rotate, you need a torque. Here's where a picture can come in really nice here. If I take that wood block, and here's its center, and let's use that word center of mass like we did way back in, I guess this is chapter 4, so I'm kind of doing the similarities of chapter 4 now, so we're kind of done with 3 and going into 4. And if I were to push it right here, and I'll just draw a straight line, if I push with a force of 100 newtons, and let's just say that this object has a mass of 1 kilogram, I would say then the translational acceleration is 100 newtons over 1 kilogram. That might be too big of a force. I wasn't pushing that hard. Maybe that's a terrible number. How about I do this? Much smaller. I was pushing with 5 newtons. 5 newtons. Even that's probably unreasonable. But the point here is I would get a calculation that says if there was no friction down here, which I do, and I push it with 5, then I would get an acceleration of 5 meters per second. That's a translational acceleration. But what I want to point out here is then the torque divided by its rotational inertia would tell me then the angular acceleration. And if you remember from our discussion here, torque is more than force. And so even though I'm applying a force of 5 newtons, look where I'm applying it. I'm applying it right through its center. So what's the distance away from its center? 0. So how much torque do I get? 0. How much acceleration, and I should say rotational acceleration or angular acceleration? 0. And so this is my way of trying to point out that just because you have a force doesn't necessarily mean you have a torque. This would be silly, but it could happen. Somebody could come up to this door and push right at the hinge. And it doesn't matter how hard they push, but if you push right at the hinge, even if I unlatch the door and I push right at the hinge, it won't open. It only opens because I did that. And so be careful here, and this is what your author's trying to say in this little section here, that, again, torque is more than force. And so just because you have a force doesn't mean you have a torque. So in this case, if you have a force and no torque, the ending result is this piece will translate, but it won't rotate. Watch this too. Maybe in comparison, I'll put it right here. What if I were to take that piece of wood, and here's the center, and this time I take two forces. So one from the string and one from these scissors. And I'll just make them 5 each again. And so I push with a 5 each way. But did you notice that for my scissors, I'm going in the positive direction, and for my string, I'm going in the negative direction. And so in a picture, it might look like this: 5 newtons in the positive direction, and 5 newtons in the negative direction. And I go to calculate what the acceleration is, and again, I should say translational acceleration. The first thing I'd have to do is to say, what is the net force? And because I have two of them, I have to combine them together. And because one is positive and one is negative, I really subtract them. And so 5 minus 5 makes 0. I can still divide by 1 kilogram, but here's what I want you to see. This would say that the net force is 0. That would say that it doesn't translate. And sure enough, I think that's what you saw, right? If I were to push, the center did not translate. But don't confuse that with it did rotate, right? So when I go to calculate the angular acceleration, I would take this force times this distance, and let me just give a rough idea of what that distance is. And so from the center out is about 10 centimeters. So here's 10 centimeters. And I go to calculate the torque from this one. It would be a distance of 0.1 meters and a force of 5 newtons. And that torque, if you look at this picture, is making it rotate in a clockwise direction. And be careful. What direction is this one making it rotate? Isn't it also in a clockwise direction? Now, don't get me wrong, the forces are in opposite direction. So that's why I subtracted them here. But the torques are in the same direction. Now, be careful with direction, right? This goes all the way back to this little subtlety, which, is, what do we mean by direction? We mean its rotation. We don't mean the direction of a translation. We mean a direction of a rotation. And so, again, that's all this stuff about rotations, I think, is a little bit harder, and that's what you're seeing here. And so I would say here that both of these forces resulting in two torques are actually in the same direction. They are both making it rotate clockwise. And so that's why I would add the torques together, not subtract them. The forces are in opposite directions. The torques are in the same direction. I won't put anything here for the I for just a second, but this, of course, 1/10 times 5 is 0.5, and another 0.5 make 1 Newton per meter divided by I, and I would get an angular acceleration. And so what I'm trying to show you here is this scenario is a scenario where I would have 0 net force. Therefore, it doesn't translate. But I have a net torque, so it does rotate. And so both of these examples are hopefully illustrating that you can have a force without a torque. You could also have a net torque without having a net force. And so if you have a net torque without a net force, you get only rotation, no translation. Whereas here, if you have a net force and no torque, you get a translation and no rotation. Now, the most common scenario, though, would be something that I just push right here. And if you look carefully at that, if I just put a force of 5, and you look at the center, you will hopefully see that I get not only a rotation, but also a translation, right? The center starting right here about where my right hip is. When I push on it, it now ends up at my left hip. There was a translational motion, and there was clearly a rotation. And so this is an example of where I have a force and a torque. There, I have both a net force and a net torque. So I get both a translation and both a rotation. I think that's pretty obvious, and people see that. But I did want you to see there are times where you could have a force without a torque, or you could have a torque, or I should say net torque, without a net force. And so that's why your author spends a moment and he says, well, let me point out a little subtlety here, because again, this whole thing of torque and Newton's second law of rotation is a little more challenging for students. Now, this would be a good time. We really probably should stop here. But I was going to say, this is where your author expands and he gets into center of masses. But since we've already gone a little bit past the time, why don't I call it good here for today? Not quite done with the chapter. I told you it was a long chapter, and I kind of figured I wouldn't get done. I was kind of hoping, but there's still quite a few more things to talk about here. We certainly haven't talked about momentum yet. Remember, that was chapter 6, and we haven't talked about kinetic energy, which was chapter 7. And so we're going to have a rotational kinetic energy, and we're going to have a rotational momentum. And so more on that, but since there's no way we can do that in the next few moments, why don't I just call it quits for today. We'll pick this up tomorrow, and then we'll have a big switch of gears. We're done with mechanics here, and this is chapters 1 through 8. And I do want to point out that I have purposely, and this is why I don't mind dragging this into tomorrow, have spent an extra long time on kinematics here, because your next class, I'm sorry, not kinematics, mechanics. Your next class is all about mechanics. It's Physics 121. And what you will do next semester, or the semester after, depending on where your math level is you will repeat everything that we have just done or doing in chapters 1 through 8. That kind of summarizes the whole semester. Now, that also means you go much deeper than we have this semester. But the reason I want to just not rush this chapter is not just because it's a hard chapter, but I really want you in a good position to succeed. I mean, I think the best thing I can do this semester is give you an extra amount of mechanics, because that's your next class. And if you don't get through that class, you won't get on to the other ones, which is Physics 122 and 123. And so after this chapter is done, we'll start talking about topics that are covered in Physics 122 and 123. But if we don't get very deep in those, I think that's okay, because you'll get those. You'll get those again in Physics 122 and 123. What I'm most concerned about is that you make sure you get that far. And so to get that far, you really have to get through Physics 121. And a lot of people, sadly, give up in 121. And so I want to make sure you have enough background, enough resources to do well in 121 and continue on in 121 here. So I have spent, like I said, a disproportionate amount of time doing mechanics. And I'm even going to let that go into one more day, because I really want you to have a strong background so that you will succeed through 121. And then this other stuff that we will learn will come back, and if there's something we didn't get to, you can learn it for the first time in 122 and 123. So you may not have realized, but that was kind of the strategy behind me structuring this class. I'll say it again, a disproportional amount of time on mechanics. But for today, let's call it quits. We'll come back and do a little more mechanics before we wrap up this chapter and move into other things.